Hello everyone, welcome back to another video example. As always, I hope you are doing well. Today we'll be covering how to calculate the P-delta effects in a multi-story steel frame. As you're going to see, it's going to be very similar to the procedure of a single-story steel frame, which we covered in the last video. However, there's going to be a couple little modifications that need to be considered. Now, before we begin, I'd like to remind everyone that the link to the PDF notes for this example can be found in the description below. Also, as this example involves using a structural analysis program S-Frame to conduct several first-order analysis, an additional link will be provided down below for a video detailing how to conduct the analysis used in this example. Alright, with that being said, let's jump into the example. Alright, so when we look at the example, it wants us to determine the design bending moments and axial load of members AB and BC in the following two-story frame using the simplified stability analysis method prescribed in CSA S16-19. So again, if we look down here at the picture, we have a nice two-story frame and it has the following loading. As we can see, we have two gravity loads, WF1 and WF2, so they are already factored. And WF1 is 55 kilonewtons per meter and WF2 is 45 kilonewtons per meter. We also have two lateral loads, HF1 and HF2, and they have a magnitude of 35 and 15 kilonewtons. So as we can see, the loading here is pretty simple, nothing too crazy. And of course, in order to do these type of analysis, we have to define our steel sections. So for all of our beams, we have W460 by 97s, and all of our columns are going to be W310 by 97s. The one thing that might scare a little bit of students off is going to be the support conditions at the base of the frame. As we can see on the outer edges, we have pin supports, and in the two middle columns, we have fixed supports. The thing to keep in mind that in these type of examples, we are going to be using a structural analysis program. In this particular case, we are going to be using S-Frame, so the influence of these conditions actually doesn't impact our calculations too much at all. Another thing to kind of keep in mind before we get into the actual example is when we're looking at this frame, both of the bays at the end, so bay 1 and bay 3, they have a bunch of moment releases or hinges. So basically, the only moment resisting frame in this case is going to be that middle bay right in the center. The other columns on the edges are called lean-on columns because they're actually not going to resist any type of lateral movement. It's going to be that center bay that's going to resist those lateral loads. Alright, so with the problem now defined, we can get into the actual calculations. The first thing we are going to talk about is notional loads, and these are going to be very important because whether you're doing the simplified method in CSA where we do a first order analysis or you're doing a second order analysis, these notional loads need to be calculated no matter what happens. So these notional loads basically account for two things. They account for uncertainty in the structure, so let's say that the structure is erected and the column is not perfectly straight. Chances are it's going to happen. We don't live in a perfect world, unfortunately. So it accounts for things like that, as well as partial yielding of the members. Of course, under lateral loads, there may be instances where some of our steel members actually yield. So this notional load, it takes into account that effect. Now to calculate the notional load, it's actually pretty simple. And the thing we're going to have to keep in mind is we are going to have a different notional load for each story in the structure. So for floor number 1, the notional load has the following formula, where it's 0.005 multiplied by the total gravity load on that story. So if we look right here, we know that for our first floor, it is subjected to a gravity load of 55 kilonewtons per meter, and that acts over a distance of 10 plus 10.5 plus 10 meters. So all I have to do is substitute that into our equation, and we can calculate the notional load for the first story as 8.4 kilonewtons. We can do the exact same thing for the second floor. It has the exact same formula, where again, it's just going to be 0.005 times the gravity load subjected to that story. In this case, the gravity load decreases a little bit to 45 kilonewtons per meter, so we can substitute everything in, and we get our gravity load as 6.9 kilonewtons. And this comes into the first common mistake a lot of students will do. A lot of students, for some reason, like to add the notional load of the first floor to the second floor. For notional loads, we do not include the load from floors above. Now, you're saying, Clayton, of course not. Why would I ever do that? Well, as we're going to see in a lot of our calculations towards the end of the example, when we're calculating these loads subjected to stories, if we have a first floor story, we actually have to account for all the loads coming above. But again, that's going to be in our calculations later. For right now, we do not consider that. If I'm calculating a notional load, it's only going to be the load on that story, nothing above. So now that we've calculated the notional loads, what we are going to do is we are going to take them and add them to the lateral loads on our structure. So again, for the first floor, we have a notional load of 8.4 kilonewtons, and what I'm going to do is I'm going to add that to the 35 kilonewtons. Same thing for floor number 2. I calculated my notional load as 6.9 kilonewtons. I'm going to add that to the second story. So again, the key thing here is once we calculate those notional loads, we have to add them to our structure in the direction that is most detrimental. So basically, since we know for the second story that the 15 kilonewtons is going left, we would also want to orientate our notional load so that it is also going left. We don't want to try and decrease these loads. So at this point right here, once we calculate the notional load, we basically have two options as a designer. We can either A, perform a second order analysis, which we're trying to avoid in this particular example, or we can perform a first order analysis and we can amplify some of those moments and axial loads using a U2 amplification factor. This option B here, that is that simplified method in CSA, and as you may guess, this is the method that we are going to do. Now, to do this method, we actually have to do two different first order analysis. The first one is going to involve gravity loads. So in our first analysis, we are going to analyze the frame solely under gravity loads. Now there's the key, solely under these gravity loads. Therefore, we must remove all lateral loads. So if I take my frame and I remove all of my lateral loading, this is what I'm going to get. And this here is what I'm going to analyze. Now there's one key thing that a lot of students forget that we have to consider before we do the analysis. To prevent any sort of sway effects, we have to add lateral rollers to each story. What happens is if the geometry of the frame, the stiffness of the frame, or the loading of the frame is unsymmetric, even under these gravity loads, our frame will have a tendency to sway laterally. We do not want this to happen. Basically, we are trying to find the effects under pure vertical translation. So what we do is we add two rollers to our story, which I'm going to call RF1 and RF2. And this will prevent our frame from translating left or right when we do this gravity load analysis. Now this is going to be important because when we look at the goals of this analysis, we basically want two different things. We want the gravity moment and axial load, which is MFG and PFG. But the second thing that we have to consider is what are these reaction forces going to be to the rollers that we just put on our structure. So as we can see, RF1, RF2, whenever we determine them, we're actually going to have to write them down because they are going to be used in our second analysis when it comes to translational loads. So as I mentioned before in the introduction, the analysis here is going to be performed in S-frame. I'm actually not going to do it in this video. If you want to see how the analysis was done, of course, I will have a video link in the description down below. Now, when I conduct the analysis, the first thing that I find is the two sway reaction forces, RF1 and RF2. And in this case, they are both equal to 0 kilonewtons. And you guys are going to say, Clayton, why is that? Isn't that convenient that it's equal to 0? And yes, it is. So here's the first trick that you can have, and this is a very good trick for an exam type scenario. If your frame is symmetric in terms of geometry, stiffness, as well as loading, these reaction forces are going to be 0. There's going to be no tendency in our frame to sway if that is the case. If we look at our frame here and we were to draw a line right down the center bay there, as we can see, the columns and beams are the same on both sides. The loading is the same on both sides, as well as the geometry of the frame itself. So because the frame was symmetric, this is why we have those 0 kilonewton reaction forces. So it's one of those nice things that if you know this is the case, you can save some time on the gravity load analysis. Now, the whole objective of this question is to determine the design forces of member AB as well as BC. So one of the things I have to do when I do my gravity load analysis is I'm going to have to write down what MFG are, and the same thing for PFG, basically the moments and the axial load due to this gravity analysis. If I were to look at column AB, or the first story column, from S-frame itself, it tells me that the axial load on this column is negative 1,025 kilonewtons. So this is basically 1,025 kilonewtons in compression. If I were to look at the axial load of column BC, or a second story column, S-frame tells us that it's negative 461.3 kilonewtons. So therefore, we are actually good to go. We don't need to consider anything else in terms of axial load. The second thing that we want to write down, however, is going to be the bending moment diagram. So for column AB, S-frame tells us that this is going to be our bending moment diagram. It starts at 70.1 kilonewtons per meter, and it goes up linearly to negative 145 kilonewton meters. So if we look here, it's nice and easy. The one tip or trick I can give you as students, don't forget sign convention. Notice that at point A we have a positive moment, but at point B we actually have a negative moment. It's going to be very important later on when we actually start calculating these second order effects. If I were to look at column BC, it's going to be almost identical in terms of the profile, but this time we start at 267.3 kilonewton meters, and then we go up to negative 293.3 kilonewton meters. Again, this is going to be important because to us, these are MFG as well as PFG. And this is really the last thing we need from our first analysis. So from here, we can move on to the second analysis, which is translational loads. So just like before, where we only analyzed our frame under one scenario, we are going to do the same thing here, but rather than gravity loads, we are going to analyze the frame under solely translational loads, or basically we remove all of the gravity loading. So basically, if we have our frame right here, we are going to analyze it under what I like to call the total translational load. Now, this total translational load is the summation of three things. The first is the factored applied loads, which I call HF, and these were given at the beginning of the question. They were 15 and 30 kilonewtons, so nothing too crazy there. The second thing we add to it is the notional load, which we talked about on the second slide. So we already know that we are going to add that to our load. And the third thing, which isn't really prevalent in this example, but something you should always be aware of, is if we had sway reaction forces from the gravity analysis, they would also have to be included here. Luckily for us, since our frame was symmetric, we don't have to include these sway reaction forces because they're equal to 0. So if I were to take my applied load for the first story and add it to my notional load, our first story load is then 43.4 kilonewtons. And for our second story, if I were to add the two loads, I get 21.9 kilonewtons. So again, this is all I'm going to add to my frame for the analysis. Again, I have no gravity loads. So the goal here for this translational analysis is to determine the translational moments and axial loads, which we call MFT and PFT. And the second thing that we want are story deflections. So this is where it's going to become a little bit different than our single story frame that we analyzed before. We need two story deflections. So if I were to take this and analyze it in S-frame, S-frame gives me the following deflected shape, and then at the very right of my structure, it gives us two deflections. It says that the joint of that first story there deflects by 24.0 millimeters, and then the second story joint deflects 37.3 millimeters. So here comes the first trick. These right here are not the story deflections, okay? So there's going to be a thing to always keep in mind. These are not the story deflections. These are the deflections of the joint. If I want the story deflection, it is going to be the relative deflection between the bottom and the top of the column. So for our first story here, our deflection is simply going to be 24.0 millimeters, basically 24 millimeters at the top minus 0 millimeters at the bottom, we get 24. So in this particular case, it was the same, but if we look at the second story here, our story deflection is actually going to be, again, the deflection at the top minus the deflection at the bottom. So it's going to be 37.3 millimeters minus that 24 millimeters, and we get 13.3 millimeters. Again, number one mistake I always see is students will take that 37.3 and use it in our calculations. That's incorrect because we want that relative story displacement. So with our story deflections known, we can move on to actually recording the translational moments and axial load. So again, you just want to draw a quick little sketch of the members of interest. And then from S-frame, I find that the axial load of column AB is 30.1 kilonewtons. So this being positive indicates that this column is actually in tension. Again, sign convention is always going to be very important. And then for column BC, it's under an axial load of 9 kilonewtons. Again, positive, meaning it is in tension. If I were to look at the moment profile of column AB, it's going to be linear again, but this time it starts in the negative region and goes to the positive region. So we start at negative 114.8 kilonewton meters, and we go up to 84.1 kilonewton meters. Same thing for column BC. We start in the negative region, move up to the positive region. We start at negative 26.5, and we go up to 47.2. Again, we want to record these because these are MFT and PFT, which we are going to be using later on in our hand calculations. So that is it for our first order analysis. Again, to do these two analyses, we typically use a structural analysis program. If you want to be brave and do it by hand, by all means, it is perfectly valid. But between us, don't do that. It takes up too much time. Your time is valuable. Make sure that you know that. So now that we have everything we need from our analysis, we can go on to actually calculating our amplification factor U2. Now, before we calculate U2, there is one critical calculation that we have to do beforehand, and it is for this factor right here, this PSE. Once you calculate PSE, you're basically good to go. This is the big boy right here. So the first thing that we can see is we need the story height. And of course, if we're looking at the first story or the second story, it's going to differ. There's one hint that for our calculations in a multi-story frame, you're going to have a PSE or a different PSE for every single story. Since we have two stories, we end up having two PSEs. So if we look at story height, this of course is going to be perhaps the easiest parameter. If we were to look at floor number 1, well, we know that the story is 6.5 meters. So I'm going to say HS1 is 6,500 millimeters. The thing here to realize, or basically one thing that students will have a lot of questions, Clayton, why do you have it in millimeters rather than meters? Well, if we look at our PSE formula, we're taking that story height and we're dividing by deflection. Since we have our deflection in millimeters, well, chances are I'm going to also want my story height in millimeters as well. If you have your deflection in meters, by all means, leave your story height in meters. Just make sure that you have consistent units throughout the equation. So that's going to be for floor number 1. If we look at the second story, it's just as simple. We just have to look at the diagram and we can see that HS2 is 5,500 millimeters. So that's a nice, easy parameter. I'm sure no students will have problems with that. Another easy parameter that we have is the story deflection because we actually calculated this on the previous slide. So we know for floor 1, delta F1 is 24 millimeters, and for floor number 2, delta F2 is 13.3 millimeters. Again, this just came from the first order analysis that we did on the previous page. You should have no problems with this. Now we're going to get into the fun ones. And I say fun like they're bad, but they're actually pretty simple. You guys are very smart people. You guys are going to laugh at how easy this is. And that is PSF. So this is going to be the total vertical load supported by each story. So what I'm going to do here, and this is going to differ from a lot of what students do, is I like to start at the very top of my structure and work down. And it's going to be very apparent why I do this real soon. So if I look at the second story right now, we know that the vertical load is going to be that 45 kilonewtons per meter, and it acts at that distance of 10 plus 10.5 plus 10 meters. So all I have to do is substitute that into my equation, and I get 1,372.5 kilonewtons. Where the trick comes in is when we look at floor number 1. If I want PSF1, well, as we can see, our first story here is supporting the load of 55 kilonewtons per meter over the same distance. However, keep in mind that our first story columns also support the load from the second story. So again, this is why I kind of hinted at back when we talked about notional loads. In a lot of these calculations, we actually have to consider the effect of stories above. This is one of the cases where we have to do that. So when I'm calculating PSF1, I have to include all the loads from above. In this case, we just have one floor above, which is PSF2, so it's not too bad. But if I had a third, fourth, and maybe fifth story, I would have to include all of those as well. So the load directly on the floor was the 55 kilonewtons per meter, but then I also have to add that 1372.5, which gives us a grand total of 3,050 kilonewtons. So again, number 1 trick, make sure that for PSF, you include the load from the floors above. Very common mistake. After here, things are looking pretty good. We can move on to a pretty hard parameter, which is the totaled factor shear. Now this one's hard if you don't know what it is, but if you know what it is, it's a piece of cake. You're going to laugh at me. So for this total factored shear, it's going to be the summation of all translational loads at and above. So there's the key there, and above the story of interest. So basically, if I was looking at floor number 2, it's going to be the summation of all the applied loads or the applied lateral loads at that story and above. So in this particular case, if we were to look at our frame, we only have one lateral load applied, which is the 21.9, and there's nothing above it. So VSF2 is just going to be that 21.9. For floor number 1, however, we have to keep in mind that we have the 43.4, but we also have that 21.9 above. This just comes from simple statics if you're wondering where it came from. It's nothing too groundbreaking, but I thought I would let you guys know, because again, the number one thing students always forget is you have to include the load from the floor above. A lot of students would just say VSF1 is equal to 43.3. That's not really true. We have to add that load from above. So VSF1 is actually equal to 65.2. So once you guys get the hang of this, again, piece of cake, everybody is laughing. The last parameter that we need is PSF-MF. So this is going to be the total load carried by the moment frame columns. So if we look at our figure here, notice that for the moment frame columns, I highlighted them in green. And this is why when we're calculating PSF-MF, it's very important to know which of these columns are moment resisting frame columns. So all we are going to do is the same process as PSF, but we're only going to take on the load carried by these particular columns. So if we look at floor number 2, based on tributary area, we know that these columns are only going to carry the load in this area. Again, it comes directly from tributary area. It's nothing too crazy. So what we're going to have is 45 kilonewton meters multiplied by 5 plus 10.5 plus 5 meters. So again, in the two bays on the side, those moment resisting columns are only taking half the load on those beams. The other half go directly to the columns at the very end of our frame. So this gives us a grand total of 922.5 kilonewtons. Then we can move on to floor number 1. Again, it's going to be the exact same procedure where we can determine the load carried by this moment resisting frame based on tributary area. But again, the trick that you guys are starting to get drilled into the back of your head is that we also have to include the load from above. Keep in mind that these two columns, column A, B, it's going to carry the load from the column above it. So of course we have to add it to it. We have the 55 kilonewton meters multiplied by the area, but then we have to add the 922.5, which gives us a total of 2050 kilonewtons. So at this point right here, if we look at PSE, we're actually good to go. We have everything we need so we can start calculating it, or as I like to call, plug and chug time, which is the best, because as you know in engineering, once you have all the variables and all you have to do is throw them into your calculator, everything is easy, everybody is happy. So what I'm going to do is, again, we have two different PSEs, one for each floor. So for floor number 1, I'm just going to substitute everything that we have, keeping consistent units, and we get PSE1 as 15,878 kilonewtons. We can do the same thing for floor number 2, again, just substituting everything that we know, and we get that it's equal to 8,143 kilonewtons. Now this is great because, again, what I said, PSE, that's the big boy we have to calculate. Once we're done calculating PSE, we can move on to the amplification factor, U2. And if we look at the formula for U2, it's simple. It only requires two things: PSF, which we already calculated, and PSE, which again, we already calculated. So you know what time it is? Well, it's plug and chug time yet again. So for floor number 1, I just substitute everything into my equation right here, and I get 1.238. So this is going to be very important when we start calculating these second order effects. For U2, for story number 2, again, same thing. I'm just plugging everything in, and I get 1.203. Now this is important because this right here is the magnitude we amplify MFT and PFT. But one little thing before we actually do that on the next slide, just notice that we are only amplifying the translational moments in axial load. We are not magnifying the gravity moments, just the translational. So this leads us to the end of our problem, which is actually determining the moment and axial load, or the design moment and axial load of our frame. You may be wondering, how do we do that? Is it a complex formula? Well, no, it's actually a very nice formula. So if we look at the design moment, we are just going to take the moment we got from our gravity analysis, and we are going to add it to the amplified moment from our translational analysis. And then the same thing for the axial load. We are going to take the axial load from our gravity analysis and add it to the amplified axial load from our translational analysis. So if we look at these formulas, we actually know everything in them. So what I like to do is I just like to make 3 schematics. The first one is going to be my gravity loads. So this is going to be my moment and axial load due to the gravity analysis, which we've already determined back in slide number 3. So again, nothing unknown here. The second one I want to draw is going to be my translational moment and axial load. And again, we already have those. They came directly from slide number 4. And once I know these two, in addition to my amplification factor, I can actually determine my design loads. So what I'm going to do is I'm going to draw the two members AB and BC, and then I can just go through and calculate everything I need. So let's start with the axial load on member AB, or that first story column. Again, all I'm going to do is take the axial load from my gravity analysis, which was negative 1025, and I'm going to add it to the amplified axial load from my translational analysis, which was 1.238 multiplied by 30.1. Again, this also emphasizes the point I've made many times now. Don't forget sign convention. Notice that for my gravity analysis, the column was in compression, but then for our translational analysis, the column was in tension. So as we're going to see, our actual design load is lower than that of the gravity load. It's negative 987.7 kilonewtons. From here, we can move up to column BC and find the axial load as negative 461.3 plus the magnified translational axial load, which was 9 kilonewtons, and we get our design moment to be negative 450.5 kilonewtons. So that's going to be it for axial load. Again, nice and simple. We can move on to the design moments. So starting at the bottom at A, we know from our gravity load, our moment was 70.1, and then our translational moment was negative 114.8, which I have to amplify. And at the end of the day, I get negative 72.0 kilonewtons for the moment at A. If I were to look at point B, but still in reference to the first story, I'm going to have negative 145 plus the amplification of 84.1. I get the moment to be negative 40.9 kilonewton meters. And if I were to draw the bending moment diagram now, it's going to look something like this, which is actually pretty important because if we look at the gravity load and translational load analysis, in those cases, the column was in double curvature. We had a transition from positive to negative moment or vice versa. If we look in this case, it starts off with a negative moment and it ends off with a negative moment. So in this case, our column is actually going to be in single curvature, which is again pretty interesting. If we go to the moments of column BC and starting at the bottom at B, what we are going to do is we're going to take that 367.3 from the gravity. We are going to add it to the negative 26.5 after it is amplified, and we get the moment as 235.4 kilonewton meters. And we can finish off this analysis by, of course, doing the moment at C. Nice and simple. We get negative 236.5, and we get the following bending moment profile. So this is exactly how you determine those design moments. Again, we do a gravity load analysis to determine the moment and axial load there. We do a translational analysis to determine the moment and axial load for there. And then finally, we add them together with some amplification to get our final design loads. Now, if we were to look at these two columns, we have the axial load in addition to the moment profile. All we have to do in CSA is just design them as beam columns. So I go check all my beam column checks. If it's good to go, the column is considered to be adequately designed. Now, the last thing we are going to talk about, of course, is how does this compare to an actual second order analysis? A lot of people know by now that CSA can be rather conservative in some aspects. So they may be wondering, well, if this is a simplified analysis, am I being extremely conservative? This is a big fear a lot of engineers have when they're designing for earthquakes. Again, the NBCC has their own earthquake simplified analysis, but it's usually extremely conservative, and most engineers opt to do the dynamic analysis. So some of you may be wondering, is this the same for CSA when it comes to second order effects? Well, if we were to look at the first order analysis that we did on the previous slide, we got the following bending moment profile and our axial loads. Now, if I were to do the same analysis in S-frame but perform an actual P delta analysis, well, it turns out we actually get the same shape of the profile. But how do the values compare? If we compare the axial load of the first story from our analysis in the previous page, we got negative 987.7, and our second order analysis gave negative 988.6. So as we can see, it's within a kilonewton. Very nice. How about column BC? Well, again, from the previous slide, we got negative 450.5, and our second order analysis got negative 450.1. So it's 0.4 kilonewtons off. It's looking pretty good for axial load, but how about moment? For the bottom moment, MFA, we got negative 72, but our second order analysis gave us negative 65.5. So it's around 5 kilonewton meters off, but as we know in design, 5 kilonewton meters, well, that's not a lot. Usually you'll be just fine with the same section for both of these. If we were to look at, again, the first story, but at point B, we got negative 40.9 in our first order analysis, and the second order analysis negative 38.6. So again, it's no big deal. And then the same thing for B, but for the second story, it's within 2 kilonewton meters. And finally, the moment at C is going to be almost identical as well, within 2 kilonewton meters. The difference between these two analyses is almost going to be negligible. Only in certain extreme cases where you're really trying to grind down the smallest section is this actually going to play a big difference. So we're looking pretty good no matter what. But yeah, that's it for this example video. Hopefully I was able to explain some of the tips and tricks that comes to calculating these second order effects on multi-story frames. And again, I hope you guys are doing well. So yeah, that's it for this video. Thank you guys so much for watching. I really appreciate it. I will see you guys in the next example video.